Now, if we are working with linear passive interconnect, which is what we're talking about today, PCB traces, backplanes, cables, connectors, you can apply something called linear superposition theory. And what this means is that you can transform single-ended parameters into differential parameters quite easily. And so differential parameters, differential-less parameters, are really what we want to use because all of these high-speed channels in the internet infrastructure are mostly differential channels. They're not single-ended. So you may start in the differential S parameter domain, and you may find a suck out like on one of the channels that Tim saw in the insertion loss. But the troubleshoot, you may want to look at the single-ended parameters because it could be that one of the lines of the differential pair has some type of asymmetry in it, and that could be causing some problems. Maybe not perhaps that suck out, but some other high loss or some crosstalk issues. So what we really want to do is jump a little bit deeper into the differential S parameters. For one differential channel, we have 2 input and 2 output. So it's a 4-port measurement. So we have a 4x4 matrix that describes how that differential channel operates. The first quadrant here is the differential in and differential out. This is how the device works in the real world. So this is the quadrant we normally go to first. Tim had looked at the differential return loss. This is differential insertion loss. Differential insertion loss is probably the first parameter you would look at in this whole matrix because it tells you the frequency response of this interconnect as a function of frequency. That's very helpful immediately to tell you something about your device. The fourth quadrant here is common in, common out. Maybe not so useful in the beginning, but it's there and we get it for free, so we can look at it later. For me, the very interesting quadrants are quadrants 2 and quadrants 3. These are what we call the mixed mode S parameters. Quadrant 2 has a lot to tell us about EMI susceptibility. So this is that case where we have a common input signal that's incident on a differential pair. And if we have a perfectly symmetric differential pair, then we should reject that. And so all of these numbers in here should be extremely low, if not 0, for a perfect differential transmission line. However, in some cases, manufacturers don't build things the way we design them. So in that case, you may have some asymmetry. You could have a solder blob that ends up on one line and not the other, or maybe a little dig in one leg of the differential pair that's not on the other. That asymmetry will cause an impedance discontinuity and a site for a mode conversion to happen so that that common energy incident on this asymmetric differential pair then gets converted into differential signal and rides along with the data so that the receiver, you have a small delta voltage that's an error introduced by that incident radiation. This is what we call EMI susceptibility, which is a crosstalk problem. Okay? Over here, this quadrant number 3 is a little bit different case where we have differential to common signal being converted. This would be if say you have that same asymmetric differential line and your signal from your transmitter is propagating a good differential signal through it, but now you encounter that same site where you had that asymmetry. Well, there's going to be impedance discontinuity there, so you know there's going to be a little bit of reflection, but you can also have some of that differential energy converted into common, and now that site will radiate. So now you could have a source of crosstalk that will contaminate the rest of your board. So there's a nice correlation between S parameter mode conversion and crosstalk that can give you a lot of hints as to not only the magnitude of crosstalk, but we can also find out where in the channel spatially it's happening. So what does a differential S parameter measurement look like? Well, here's a case where we have two different channels. One has a standard via and one has a micro via. Micro vias are just smaller in diameter. You either use a smaller drill bit or use a laser, and so that has less excess capacitance, so you get better performance because you have closer to a 50 ohm or 100 ohm differential transmission line. And so starting with differential insertion loss, this is the blue and the red curve that come over like this. And here you can see the micro via has slightly better performance at high frequencies because of this smaller via. And so differential insertion loss, you want that to be as close to a flat line as possible. If it were perfect and no loss, it would look like that as a straight line. Differential return loss, on the other hand, is the reflection. And so these two curves here, there's a lot of moding going on here, but it starts at a very low frequency with a very low signal because there's not much reflection down here. And as you go to higher frequencies, you get more and more reflection. And so you normally want to look at the top lobe of these family of curves here and just see how it rolls up. And you can see how you get more reflection as a function of frequency. So this is a typical measurement of a couple channels looking at differential S parameters.